In this videocast, we're going to talk about ionization and as it pertains to acids, and we'll also talk about colligative properties. So we talked about dissociation before, where we had sodium chloride dissociating the sodium ions and chloride ions. We can call that dissociation, or we can call that ionization, because that's really what we made. We made a bunch of ions from this solid substance. So ionization, dissociation, potato, we're talking about the same thing. If we're talking about acids, we could talk about the ionization of hydrochloric acid, and it would ionize into hydrogen ions and chloride ions. So specifically with acids, all acids have to have that hydrogen, but when we talk about acids in our next chapter, we're going to be referring a lot to the hydronium ion. And you've had to memorize this ion on all your polyatomic ion quizzes, and I would either accept H3O plus or H plus. And I told you there would come a day when you would have to know the difference. Before the time being, I would take either one. Well, that day has come, and you need to know the difference between a hydrogen ion and a hydronium ion. A hydronium ion is H3O positive. The reason why I would either accept H plus or H3O plus is because all hydronium is a hydrogen bonded to water. This H plus that is given off by an acid is real attractive. It is so attractive that it is not going to be alone for very long. And this chapter is all about aqueous solutions. And when we have an aqueous solution, we have a lot of water. So for the most part, that hydrogen ion is going to bond with the water to form that hydronium ion. So it's just a hydrogen bonded to water. That's what hydronium is. So here we go. The hydrogen ion attracts other molecules or ions so strongly that it does not normally exist alone. So a better way of writing this ionization equation up at the top, where we have hydrochloric acid splitting into hydrogen ions and chloride ions, is we're going to bring water down into the equation, because water does play a role. We've got this happening right here, where the water is going to attach to that hydrogen, and it's going to happen pretty immediately. So instead of just having water written above the arrow here, water plays a role. So we're going to bring that down and make it a reactant. And what we end up having it looks something like this. The HCl separates or ionizes or dissociates, whatever we want to call it, and the hydrogen is attracted to the water and bonds with it to form the hydronium ion, that H3O plus, and chloride ions. We'll deal a little bit more with this when we talk about acids and bases, but I wanted to give you a heads up, because when we do talk about acids, we will talk about the hydronium ion. And you need to know that it is that hydrogen bonded to a water. All right. Now, when we talked about solutes being dissolved in solvents, I said that solutes could either be electrolytes or non-electrolytes. Non-electrolytes are molecules. They're things that aren't made of ions, so they won't split into ions. Electrolytes split into their ions, or dissociate, or ionize. And that's what will carry that electrical current, making them electrolytes. Well, there are actually two different types of electrolytes, and it's all in the way that they split up. There are strong electrolytes and there are weak electrolytes. Strong electrolytes ionize 100% in dilute aqueous solutions. So that means every single bit of the compound splits up into its ions. Water can get in between all of them. Acids, strong acids, hydrochloric, hydrobromic, hydroiodic, also perchloric, sulfuric, and nitric acid are all strong electrolytes, and nearly all ionic compounds that will dissolve in water are strong electrolytes. Weak electrolytes do not ionize completely in aqueous solution. I like to think of weak electrolytes like the high school relationships that we see often, where they're together and then they break up, and then they get back together and then they break up, and then they get back together and then they break up, and it's just a never-ending cycle. That's what's going on with weak electrolytes. Basically, the ions are attracted to each other, and then they get confused by water and its polar nature. And so they break up. They're like, oh, I'm attracted to water. And they split up because they're attracted to water. And then they're like, wait, we're attracted to each other. And they get back together. And then they're like, ooh, but water. And they split up. And then they're like, wait, we're attracted to each other. And they get back together. So if you were to take a snapshot of an entire container of a weak electrolyte, what you would see is some ions floating around, because some of them have been confused by water and have split into their ions. But many more of them have already gotten back together. So you don't have as many ions running around in that solution. An important weak electrolyte to know is acetic acid. Now you know acetate as C2H3O2. And that's what we have right here. It's just written out a little differently. This is how organic chemists write it. Inorganic chemists write it the way that I've taught you. And then we combine it with a hydrogen to make it an acid. But you should be able to recognize it either way. And for this, it would look something like that. No charge. Hydrofluoric acid is also a weak electrolyte. Now we're going to talk about colligative properties. Colligative properties depend on the total concentration of solute particles, not their identity. So it doesn't, and we're talking about adding a solute to a solvent. And what these properties solvents are going to exhibit when you add a solute to it. Now these properties, it doesn't depend what we add to it, it depends on how many pieces it splits up into, or how many pieces it ionizes into. So that's the important part when we're dealing with colligative properties. There are 4 things that exhibit colligative properties. Vapor pressure is going to be lowered. The freezing point is going to be lowered as well. We call it freezing point depression. And our boiling point is going to be elevated, or it will increase. All of that happens anytime you put a solute in a solvent. Now, for simplicity's sake, we're going to be talking about water as our solvent, so this chapter is all about aqueous solutions. So anytime you put something in water, it's going to have a lower vapor pressure. It's going to have a lower freezing point and a higher boiling point. We're also going to change its osmotic pressure. I'm not going to talk a lot about osmotic pressure. It does have to deal with osmosis, and you discussed that a lot in biology. Osmotic pressure is the pressure it takes to stop osmosis and stop the movement of the solvent particles through that semi-permeable membrane. But the first 3 I am going to talk about. The first one is vapor pressure lowering. So the vapor pressure of a solution is lower than that of a pure solvent. Vapor pressure, if you'll remember, the prop I use all the time with this is a water bottle. If you have a closed system, some of the particles from the surface of the liquid will evaporate, and those vapor molecules will bang on the walls of the container, creating that vapor pressure. So in effect, the vapor pressure is a measure of the tendency of the molecules to escape to that vapor phase. The higher the vapor pressure, the lower the intermolecular forces, so the easier it is to escape from that vapor, or from the liquid to the vapor phase. Now, I got a picture here that'll help you understand it, hopefully. I have a flask here, and I just have my solvent in here. Let's say these are little water molecules. So it's just full of water and nothing else. In the other flask, I have a solution. So I have my water, which are represented by the little blue molecules, and these huge solute particles. Our solute particles tend to be pretty large compared to tiny little water molecules. Well, in the pure solvent, remember, for evaporation to happen to create this vapor pressure, some of the particles from the surface will gain enough energy and they can escape their attractive forces and become a vapor. But that can only happen at the surface. If you look at the solution, so with the blue and red dots, you'll see that the solute particles, these red ones, take up space not only within the liquid, but also at the surface. So not as many water molecules can get to that surface to evaporate, because that's the only place evaporation can happen. And so what happens is, because those solute particles are blocking the surface, not as many particles can escape to the vapor phase. And since you don't have as much vapor, you have lower vapor pressure. And I think that's what this says. A non-volatile solute. Now, volatile means that it is very easy to evaporate. We have to talk about this principle with non-volatile solutes, otherwise they're evaporating and it's changing our concentration all the time. So we just say it's a non-volatile solute, something that doesn't easily evaporate. Lowers the concentration of water molecules at the surface, and therefore lowers the tendency of water molecules to escape to the vapor phase. So that should explain vapor pressure lowering. The vapor pressure becomes lower because not as much solvent can evaporate. Now, freezing point depression. Anytime you add a non-volatile solute to a solvent, the freezing point is lowered. We have an equation to go along with that, and it's lowered by a certain amount, and it depends on what the solvent is. Again, since we're dealing with aqueous solutions, we're going to be talking about water as our solvent. So we have this constant, Kf, for freezing, and we use K for constant a lot. For water specifically, is 1.86 degrees C per molal. So for every solution that we make, we put 1 molal of a solute in a solvent or in water. We're going to lower the freezing point by 1.86 degrees Celsius. So that's pretty significant. And we can figure out what's going to happen to our freezing point depending on the concentration or the molality of our solution. In working problems, you're going to use the Kf of the solvent. For this class, we're just going to be working with water, so we'll always use that 1.86 degrees C per molal, but if you had a different solvent, you would just need to look up the Kf for that solvent. Freezing point depression is going to be represented by delta Tf. Now, we've seen delta before, that Greek letter, and it means change in. And then we have T, which means temperature, and then the little sub F means freezing. So it's our change in freezing temperature. And it can be found by this equation. Delta Tf equals I times Kf times molality. So we'll outline each of these. So again, change in freezing point or freezing point depression. I is going to be the number of pieces the solute splits into. Now, we've been splitting up our electrolytes a lot. You may not have realized that, but we've been splitting up our ionic compounds into their ions a lot over the past few days. And that's in part to give you this Van't Hoff factor, the I. If I have something like, let me try and make this a little bit darker. If I have something like NaCl, and I put it into water, it is going to split up into its ions. So it splits into 2 pieces. So that would be my I for sodium chloride. I would be 2 because it splits into 2 pieces. If my solute was calcium chloride, it splits up into calcium ions and chloride ions, and then I have to balance, so 2 chloride ions actually end up. So I have 3 pieces, 1 calcium and 2 chloride ions that are floating around in solution. So my I for calcium chloride would be 3. If it is a non-electrolyte, meaning it's not made of ions, and that might be something like sugar, and I dissolve it in water, it does not split up. What you end up with is just sugar in aqueous form. That's what that says, aqueous. And so it doesn't split up, so I get, for every 1 piece of sugar I put in, I get 1 piece floating around. So for non-electrolytes, your I is equal to 1 because it doesn't split up. Okay, so hopefully that explains where you get I from. You have to look at the compound, at the solute, and see how many pieces it's going to split up into, so, or how many ions. All right, back to the equation. Kf is your constant for your solvent, and M is your molality. So moles of solute over kilograms of solvent. Now that we know what all of these are, we can go and work a problem with this. So, determine the freezing point of a 0.289 mol water solution of table salt. So, I'm going to work with this one. I have my equation there, so I'm going to look for my change in freezing point. I is the number of pieces that the solute splits into. So NaCl would split into sodium ions and chloride ions, a total of 2 pieces, so my I is 2. Then I'm going to multiply it by my Kf. This is something that would be given to you. And for water, it's 1.86 degrees C per molal. And then I plug in my molality, 0.289 molal. Molality cancels out. All I'm left with are degrees C, and that makes sense for a change in temperature. And I end up with 1.08 degrees C. That means my freezing point was lowered 1.808 degrees C. Notice the way the question's worded. I did not ask for how much the freezing point was lowered. I asked, what is the freezing point? Well, water normally freezes at 0 degrees C, and anytime you add something to it, it freezes at a lower temperature. So this time it's going to freeze at 1.08 degrees C lower than it normally does. So my new freezing point would be negative 1.08 degrees C. It makes it easy for water, but if it was another substance, then I would just find its freezing point and then subtract the change in freezing temperature. All right. Now, that's freezing point depression. It also is going to elevate the boiling point. So this same solution of salt water is not going to boil at 100 degrees C. It's going to boil at something a little bit higher than that. And the equation is going to look very, very similar to what we have here. But you're going to notice here with our Kb, constant for boiling for water, it's smaller. So it affects the boiling point less than it does its freezing point. So my Kb for water is 0.51 degrees C per molal. Here is the equation. The equation looks exactly the same, except instead of little sub f's, we have little sub b's, and because we're talking about boiling instead of freezing. All the units are still defined the same way. Delta TB is your change in boiling point or boiling point elevation. So with that, we can go ahead and work a problem with this one. This time I'm asking, what is the boiling point elevation of a 1.88 molal aqueous solution of calcium chloride? Well, we want to first write the formula here for calcium chloride. So calcium is 2+, chlorine is negative. The sum of the oxidation numbers is not 0. So I end up with calcium chloride, CaCl2. I'm going to be solving for delta TB, my change in boiling point. And now I need to figure out what my I is going to be. Calcium chloride is going to split up into calcium ions and chloride ions. But how many chloride ions? 2. So for every 1 piece of calcium chloride I put in, I get 3 pieces floating around, 1 calcium and 2 chloride ions. So I is equal to 3. Now Kb is given to you. And my molality is here in the problem. Then we're going to multiply all of those together. 3 times 0.51 times 1.88. And I end up with a delta TB of 2.88 degrees C. That means my boiling point will be elevated 2.88 degrees C. So that answers this question. But if I were to ask what will be the new boiling point of this solution, remember boiling point always goes up. It is elevated. So water normally boils at 100 degrees C, or pure water does. And my boiling point is now going to be changed. It's going to be higher by 2.88 degrees C. So I'm just going to add it, and it would be 102.88 degrees C would be my new boiling point. All right, those are colligative properties. Not too bad, and hope this helps.